motion. The first idea that we've got to have down, and it doesn't matter what type of motion we're talking about, if we're talking about displacement or velocity or speed or acceleration, doesn't matter. The x-axis is always time. So, once we've established this idea as constant for all of our graphs, the next piece is we're just going to talk about individual types of motion graphs. So the first one we're going to have up is displacement versus time. Versus time. Okay? When we're talking about displacement versus time graph, it's very important to recognize this is displacement, not distance. Why is that going to be significant? Negative values. Excellent. So when I set up my graph, I've of course got time on the x-axis, displacement on the y-axis, and I need to show that my my y-axis can be negative. I'm just going to go through and put some marks here to show roughly equal amounts of displacement and time. Don't tell your math teachers that we're just kind of eyeballing it. Okay? So, for the purpose of this, a couple of things that we want to make sure we understand. As it was said, this is displacement versus time, and therefore we can have negative values. It also means that we don't continually increase in value. If we were talking about displacement versus time, distance versus time, a distance versus time graph always increases. Displacement versus time picks one location that's 0 and can come back down. So displacement versus time can come back to 0. Distance cannot. All right, so for the sake of just having an example here, can I ask Zane to stand up? All right, Zane, you are currently standing on a yellow tile. We are going to call that yellow tile 0. Could you walk back to the next yellow tile? Like big square? Perfect. So Zane's walked back one yellow tile. We'll call these each increment a yellow tile. It took him, let's say, a second to do that. So he's traveled 1 second. He's now going to stand there and mill around doing nothing for about 2 seconds. Perfect. You're doing great, Zane. Now, one of the limitations of a displacement versus time graph is it only shows one dimension. So if Zane decides to walk over and talk to Asia for a bit, there's no way I can show that on this graph. I have no way of showing that he has walked to his right. It just shows that he's continued to stay standing and in place. And as far as I know, based on this graph, he's still standing next to Secor. Okay? You can go back to your seat. Thanks. And as he walks back to his seat, it takes a couple seconds, and he reaches that original position of 0. Okay, so our next point. How do I show stationary on a displacement versus time graph? A straight, flat line. Okay, straight, flat line shows stationary. Or, what's my alternative to stationary in this case? Moving in another dimension, yeah. Where are my football players in the classroom? Like, none of you? Really? Wow. All right, how about people who watch football and are interested in it? All right, there we go. So when we talk about progress for a play, we talk about how many yards a play is gained, right? So all we're doing is we're talking about displacement along the y-axis. Nowhere in the football statistics for a play is it going to tell you how many yards they moved laterally. No one cares. They only care how much further you brought it down the field, how many yards gained, if you made it to a new first down or a touchdown, something to that effect. Nowhere do they keep track of data as to, well, yeah, he caught the ball and then he ran 7 yards to his right, making no progress down the field. No one cares. They just say he didn't make it anyway. Make sense? So we're keeping track of the same information here. He made it 1 yellow tile, and he stayed in place, and then he came back. Okay? Our next piece here. In math, how do you determine slope? Rise over run. All right, so M, or slope, is rise over run. Or change in Y over change in X, right? That's point slope form. Okay, so in this case, what is rise? Just what's the variable? Displacement. Okay, and what's run? Where have I seen that equation before? The velocity equation. It's right there. It's in the worksheet packet. So what this means is that on a displacement versus time graph, the slope is always the velocity. At any point. And to reinforce that idea, what is the slope of a flat line? 0. And how fast was he moving when he was standing stationary? 0. So the slope of the displacement versus time graph at any point is the velocity. All right, so I'm going to get up and move back and forth, and I want you guys to try to record the same motion that I'm going to move, and it's going to be a little bit more elaborate than Zane's here. Try it on the same graph. Grab a different color writing utensil. I moved forward for 4 seconds. I stayed stationary. I moved forward again for 1 second. I came running, or not running, but I came back to the 0 mark, and then I went beyond the 0 mark. But what did I do? Slowed down. How can I show that I slowed down? Just draw it slowly. Not as steep. Okay, you're right. I'm going to need to go negative because I came into the negative zone. But I'm also going to need to curve the line. I'm going to need to curve the line because I was getting progressively closer and closer to 0 velocity. Meaning that I need my line to get progressively closer and closer to 0 slope. So in order to show that I came to a stop and that I was decelerating, I need to curve the line. So curved line shows an acceleration. If it's curving to a lower slope, then you're slowing down. If it's curving to a higher slope, you're speeding up. Okay? It doesn't matter if it's getting more positive or more negative. Getting greater absolute value is faster. Getting lower absolute value is slower. Good? Okay, our next type of graph is a velocity versus time graph. Now, I'm just going to try using the same orange motion that I just went through. But now, instead of having displacement on my y-axis, it's going to be velocity. And putting in these marks again. All right. How can I find my velocity based on my displacement versus time graph? Rise over run, the slope. So initially, my slope would have been up 2 over 4. My slope would have been a half. And I was at a half for 4 seconds. So 1, 2, 3, 4. So there's already a difference that we can tell here. In a displacement versus time graph, what did a flat line mean? Stationary. All right. Am I moving in this case already with the velocity versus time graph? Yeah. So flat line doesn't necessarily mean stopped. It does mean constant velocity. So flat line is a constant velocity. All right, but then I did stop. So how am I going to show that I did stop on the velocity versus time graph? How am I going to show that I did stop on the velocity versus time graph? Go back to 0. So I'm going to hold right at 0 for a second. The only way to show something stops on a velocity versus time graph is for it to be at 0. On v versus t is to be at 0. All right. Then I went back up to a 1 meter or 1 block per second speed for 1 second, and then I changed to a negative value for 3 seconds, and then I came to a stop. All right. When we talk about velocity versus time graph, a negative value means I'm moving the opposite direction. Just because I had a negative value up here didn't mean I was moving a certain direction. Here it does. Negative values show motion in the opposite direction. All right, here, up in the displacement versus time graph, how did I show that I was slowing down? The curve. Here, how does it look like I've showed that the velocity was changing? All right, it goes back to 0, and I have a slope. Again, m is rise over run, or slope is rise over run. What is my rise in this case? Velocity. What is my x-axis, or my run? So rise, or velocity over time. What's velocity over time? Acceleration. So what's the slope of a velocity versus time graph? Acceleration. Versus time graph is acceleration. All right, questions about either of these two graphs that we just worked through?